That's not quite what happens if we start with a switch code, though, because in our code, we manually set up this jump table as a local table, and that's why it got registered relative to RSP. When the compiler is the one generating the jump table, like in our original switch form, it will statically generate a table. Not on the stack, but just in read-only memory. So that's why if you look at -s output from switch-eg, you'll see a section RO data. It's 8-byte aligned because we want to use these as 8-byte values, 8-byte addresses, and so the alignment makes it better. And it has all of these labels. Instead of making up specific numbers, it lets the linker and assembler work together to make sure the code is put in a good place. But it makes one label for each of those places that we need to jump to, and in particular it lines them up 0, 1, 2, 3, 4, 5. So remember 5 and 6 go to the same place, so that's why L7 is the same there. The setup for switch-eg is going to take that number x and do a comparison to 6. So remember, we need to check whether x is 1, 2, 3, 5, or 6. X is a signed number, so if it's negative or if it's greater than 6, we need to jump to the done label. What we see is the generated code has an unsigned interpretation of the result. And that's because if we have a negative signed number, it'll turn out to be an unsigned number that's way bigger than 6. So it's sufficient to jump to done as long as we get to any number that's bigger than 6 unsigned. We jump to the part after the switch as label 8. We'll also jump to that same spot if x turns out to be 0, because our JA doesn't capture the 0 case. So bigger than 6 is unsigned, or 0, we'll jump to label 8. Otherwise, we do this similar sort of calculation. And you see the notation here is saying L4. L4 is the label for where we put that read-only jump table, and we use RDI times 8 for the same reason that we had before. Right, we want to index into this table where each element is 8 bytes long, so we need to take our index and multiply it by 8 to get the right address. This table then will be set up to correspond to the machine code that's generated for the body of the switch. So L3, for example, will correspond to where this code starts, and L9 will correspond to where the case 3 code starts. 5 and 6 jump to the same place. 4, we need a case for 4 in our jump table because our pretest only looked for greater than 6. And so 4 needs to be explicitly mapped like 0 down to label 8. Of course, it's not the C code that these are mapped to, but the generated assembly code will have those labels surrounding the different branches. If we jump down into one of those branches, recall that 2 and 3 map to labels 5 and 6. Let's look at the label 2. So we go to the case for x equals 2. The original C code had w equals y divided by z. The div instruction is a little unusual. It takes its arguments, it really needs 3 registers, 2 for the thing to be divided and another one for the thing to be divided by. And we only mention the register that we're dividing by. Z is an RCX here. Y we take and we copy into RAX, and then this CQTO spreads out or extends RAX to also cover RDX. So RDX and RAX together are the implicit destination argument for IDIV. So that means RAX ends up with the division, and in that case, after RAX has a division, we just need to add Z to it. So in the 2 case, we end up with a jump, even though it looks like fall through in the code, to add Z after doing the division. Meanwhile, case 3 over here, which is L9, was that right? Let's see, case 3, yes, L9, okay. L9 moves 1 into EX. So what the compiler's done is seeing that there was initialization to W, but case 2 ignores that initialization and does a fresh computation. So it rearranges things and moves the W equals 1 to just case 3, and that's why we end up with not a simple fall through, but a more complicated fall through. Both 2 and 3 get to this case to do the finishing up, adding Z to W, and then just returning because W is stored in RAX anyway.